Okay, so we just learned how to perform partial fraction decomposition on a proper rational with distinct linear factors. So we're always doing proper rationals, but this part was an extra hypothesis, distinct and linear. So we have to investigate in the rest of the chapter what to do in those other cases. But basically, if you understand what we were doing so far, then the rest of this is just the same thing carried out in slightly different circumstances. So you'll have slightly different looking forms for your partial fraction decomposition. So we need to decide what to do when instead of a linear factor, we have an irreducible quadratic factor. The standard textbook irreducible quadratic would be the polynomial x squared plus 1. It does not factor. And then we have to understand what to do if instead of distinct linear factors, we have repeated ones. Okay, so let's first of all look at what to do when we have irreducible quadratic factors. Okay, so first of all, recall that any linear factors like these guys in a partial fraction decomposition have a nice looking antiderivative. Okay, so every time you see a single power type thing in the denominator, you should be thinking natural logarithm. Okay, so these sort of building blocks of rational functions all go with natural log antiderivatives. Okay, now when we're looking at irreducible quadratic factors, we're going to have to understand what sort of antiderivatives go with those building blocks. Okay, so first of all, let's make sure you understand what a irreducible quadratic is. So a quadratic has its coefficients a, b, and c like this, and it's irreducible when the part that's under the square root in the quadratic formula is negative, which would mean a negative number under square root gives you an imaginary answer. Okay, so these are the quadratics with no roots. What that means is graphically, these are the parabolas with no x-intercepts. They open upward, and the x-axis is below them. Okay, so let's see what happens when we have one of those and we try to integrate it. Okay, just like we know already what happens when we have one of these and we try to integrate it. So let's see what happens with this guy. So first of all, is this going to be an irreducible quadratic? Well, all you need to do is take a look at the b squared minus the 4ac. So b squared is 36. And then we have minus 4 times 1 times 11. So that's certainly negative. So this is irreducible. Okay, so our conclusion, that's what we use the arrow for, is that it's irreducible. Okay. So this is exactly what we wanted to look at. You should convince yourself that any sort of obvious u substitution here is hopeless. There is no x dx which would accommodate a u substitution of an x squared. Okay, so there would be no way to transform this to look something like this, which we could integrate. Okay, so this, even though it looks pretty benign, is something that we haven't given you before in Calc 1 or in Calc 2 to integrate. Okay, although we have seen some hints about how to handle it when we were talking about trig substitutions. So recall that any quadratic can be written as one of these forms by completing the square and using a u substitution. Okay, so actually these ones here are what you get for irreducible quadratics. Quadratics, I can't quite squeeze it in there. Okay, so let's see if we can recall how to do that. So let's first of all complete the square. So I've got my x squared plus 6x plus 11, which I want to start thinking of as an x squared plus 6x plus something else. to complete the square, right? So what would I have to square in order to end up with an x squared plus 6x? Well, if I had an x plus 3, then FOIL, when I did FOIL on x plus 3 squared, I would get x squared plus 6x, right, plus a 9. So I would want a 9 there to make this look like a square. And that means I have to cancel it out with a 9 over here. And now I write it as the square, x plus 3 quantity squared. And out here it looks like I have left over a 2. Okay, so this integrand can be replaced with 1 over x plus 3 squared plus 2 dx. You notice it's already starting to look like this situation right here, okay? And that means we're going to want to use a u equal to x plus 3 to make it look exactly like that, because this whole part will just be a u squared. So our du is just a dx, and we end up with 1 over u squared plus 2. Okay, so this is exactly the sort of scenario that we would have been in chapter 6.6. So I guess it's not entirely true that we haven't done these before. It's just that we haven't done them in this disguised form before. We had to, do this tricky completing the square and u sub to make it look like it. Okay, and if you remember, this is basically an inverse tangent integration. So maybe I'll recall the formula over here. This would be, for instance, something on your formula sheet. Du is equal to 1 over a inverse tangent of u over a plus c. So in this case, my a would be a root 2, since I need an a squared right here. So I have 1 over root 2, and I prefer arctan of our u over a, so u over root 2, and plus our constant of integration. Okay, and of course we substitute back into x's. Anyway, my point is that arctan is now of a very important status, more important than any of the other inverse trig functions. This guy right here was one of our standard building blocks for our partial fraction decomposition, and it integrated to a natural log. Now that's going to be the exact same sort of scenario that we have for irreducible quadratic building blocks. Okay, so when you have things like this and we integrate them, you should expect arctan to come up. Okay, and that's for irreducible. Okay, so irreducible quadratic denominators lead to arctan. Okay, in the same way that linear denominators lead to natural log. Okay.